real to bib optics. Please join me in welcoming Shlomi to the stage.
I will present our paper, collaboration between me and Pharr from Bilinear. This paper continues our research on performing practical wave simulations in complex realistic settings with applications for rendering, wireless signal propagation and coverage, acoustics, and so on. And today I will talk about generalizing the classical path integral formulation of light transport to general purpose wave simulations that are both accurate and practical enough for the mentioned applications. The classical path integral formulates the response of a sensor as a sum of independent contributions over all possible finite light passes connecting an emitter to the sensor throughout the scene. One such path is illustrated. A lot of our modern day rendering builds upon this very formulation, and it has been shown to scale well to the complex scenes and environments that we see in movies and that we care about. Our goal is then to generalize this formulation to something that actually can do efficient wave simulations. And to that end, we start by asking two questions. First, what is it that makes this formulation practical and scalable? And we wish to identify the driving characteristics in order to preserve them as much as possible in a generalization. We recognize two crucial properties. First one is locality. Locality means that at any point in time a light particle exists at a singular position and propagates into a singular direction. Such a particle traces classical rays through space and interacts with matter at singular points. Often it interacts with just a small fraction of the scene, and therefore we are able to make good use of accelerating data structures to speed up propagation. Second characteristic is incoherence. In this formulation, particles sum up linearly, meaning incoherently. Distinct particles do not interact with each other and cannot annihilate one another. This means that once a good path is sampled, its contribution will always remain part of the solution. It will not be taken away, it will always be there, and when sampling constructing passes, incoherence allows us to construct one pass at a time and forget about all other samples. A lot of the sampling techniques, the powerful techniques in computer graphics, implicitly assume incoherence for their effectiveness. And I would argue that these together are the two properties that define the classical path integral and path tracing, and are what enables the derived methods to scale to the complex scenes that we want to simulate. Okay, so knowing which properties we wish to preserve, second question before we generalize is what actually can be simulated using the classical formulation. It is insightful as it would guide how we generalize. With little detail, I will mention that classical path tracing may reproduce some particular wave effects beyond geometric optics with good generality. Some, like color, are rather trivial, but some do depart strictly from a classical model that is devoid of interference phenomena. So we feel that the question, what actually can be formulated using a classical formulation, has not been given the attention it deserves, and in our supplemental material, we rigorously and formally set limits on the reproducible phenomena under classical path tracing. It is important to understand our tools before we build new ones. We show that what can be simulated indeed goes a bit beyond geometric optics. We may reproduce, in expectation, phenomena that arise from stationary wave ensembles interacting with stationary material models. Please see the supplemental material for details. More relevant to this talk is the fact that important non-stationary effects like diffraction by explicit structures or geometry cannot be reproduced without making sweeping and limiting assumptions, as well as some other phenomena. And crucially, we show that we may not do better with a local and incoherent path formulation. This is a hard limitation. So with more information in hand now, we know that we do indeed need to generalize the classical formulation into something that can reproduce the phenomena that we want. And that means that perfect locality or incoherence must be given up, and yet we should remember that these two properties are important for efficiency. So what we're going to do is try to give up as little as possible. We start by sacrificing incoherence and introduce the bilinear path integral. It's local, meaning we continue to ray trace, but not incoherent, meaning that distinct particles do interact with one another. In our bilinear path integral, contributions are summed up over every pair of passes, and we consider their mutual contribution, formalizing the fact that particles interact. In contrast with the classical setting, the mutual contribution function here may take negative values, and see the paper for more details. I will note tangentially that bilinearity is enough for electrodynamics because only bilinear interference terms ever arise. It's not an approximation, higher order terms never need to be considered, so we can understand the bilinear generalization as indeed the smallest departure from the classical setting. Wave simulation methods that fall within this domain are some of the most common ones that do exist today, and include all the geometric theory of diffraction-based approaches, mutually interfering rays, as arise in some computer graphics methods. A few important ones are listed. This formulation enables casting existing methods into a path tracing-like framework. We do know that such bilinear methods scale poorly, considerably worse than classical tools. And this formulation makes it evident. From this integral, you may note that just sampling individual good passes is not good enough. You now need to sample passes such that no other pass through the scene will destructively interfere with your original sample. Pass sampling is now always a global problem. We show that by performing a very simple experiment, light is diffracted by simple geometry, and we render a diffraction pattern displayed on the right. We zoom in upon the marked area on the bottom right and show the pattern after 2 samples per pixel using one of our incoherent methods and a bilinear framework. Of course, there is noise, but unlike ours, you may note that the bilinear method fails to reproduce any pattern, but only injects high-intensity noise into the scene. The bilinear framework requires an order of magnitude of additional samples to destructively interfere with the previous samples in order to take that erroneous injected energy out of the scene. And of course, this gets rapidly worse with scene complexity. So our primary purpose with this bilinear generalization is to highlight how sampling becomes more difficult, effectively a global problem. Such frameworks do not scale well. We leave for future work to consider how to sample passes under bilinearity. It's a pretty difficult problem, but it can be quite interesting as, again, bilinear frameworks do exist in the wild. We leave bilinearity. We try generalizing by sacrificing incoherence. We do get important theoretical results, but it appears a suboptimal solution. Based on our discussion, there is another approach we could take. Let's forego perfect locality. So now we will generalize a classical integral to a weakly local but still incoherent formulation. Weak locality means that instead of a point particle, we define a particle now to exist in a small region of space and propagate into a small solid angle. Of course, I'm describing just a beam of light. Transport is now region to region instead of point to point. A rigorous and formal expression is given in the paper. For the light transport optics, we use a theory we have developed previously, cited on the right. It remains unchanged, so our electromagnetic beams are Gaussian beams. We achieve weak locality with these beams by cutting off their Gaussian negligible tails. And in this paper, we simply show that the geometric envelope of a Gaussian beam is an anisotropic elliptical cone, and the two things are dual. A Gaussian beam uniquely defines its elliptical conic envelope, and conversely, the elliptical cone uniquely defines the Gaussian electromagnetic field, which is very convenient because tracing these weakly local beams reduces to tracing the simple elliptical cones that act as geometric proxies. I will briefly overview how a wave tracing framework that builds upon our weakly local path integral works. We start with sourcing a beam from an emitter or a sensor, see the paper for details, and trace the geometric proxy, the elliptical conic envelopes of space, till we intersect geometry. The underlying well-defined electromagnetic field interacts with the surface materials in the geometry. and we construct on the fly a BSDF in effect that quantifies the angular scattering power distribution, from which we may sample a scattered beam and continue to contrace. Conceptually very similar to the classical path tracing, with some obvious unique challenges. From the geometric perspective, we need to contrace and intersect arbitrary anisotropic elliptical cones with primitives, and we wish to use accelerating data structure as before, right? What works for rays is not exactly the same that works for cones, and we do a deep dive in a recent publication, and the work there is used today by our wave tracing framework. There are also other typical annoyances with contracing, like the difficulty in exploring narrow regions of space, like a waveguide. We introduce ballistic propagation for these purposes, see the paper. From the wave simulation aspects, we now deal with interaction regions, in contrast to points classically. What this means is that multiple materials and geometry can interact with a single beam. We need to deal with cross-material interference terms that do not arise classically, and we need to import and sample from an aggregate total interaction. We do present an important, very general important sampling strategy for the interfering interactions. This is important because it solves the sampling of the interference terms. Still, we need to model the wave-based interactions of our beams with surface materials, triangles. Such material models remain severely lacking, and this is a problem that transcends our setting and is very broadly applicable to wave simulation and even classical predictive rendering. As an example, a physically sound practical model for something as conceptually simple as scattering by statistical rough surface remains missing. For additional information, I encourage you to attend the talk by Matthew tomorrow. Anyhow, in this work, we do not propose a new material model. We discuss some theory and make important connections to classical SDFs. Finally, we have released a weekly local wave tracing framework. The current release 0.1 is still very alpha. Not everything is perfectly implemented, but we are working on a 0.2 release later this year, where we improve upon the published work. We can render, of course, simple Cornell boxes, for example, with diffraction apertures, and you can see diffraction patterns that arise. Wave simulation happens throughout. Some effects are less noticeable. It is more interesting to consider longer wavelength simulations where wave effects are dominant. This is a city scene. It's a full 3D scene viewed from above, buildings in gray, and we visualize the logarithmic color-coded intensity that falls upon the ground. 1 gigahertz emitter is placed at the top, as the yellow dot is. You might be able to see it. This is the wave optical, and this is the ray optical results, and the difference is pretty big. The difference arises not just in the shadowed regions, but you might be able to see some areas where the ray optical results massively overpredicts the incident irradiance, because light that should have diffracted away did not, because it is a ray optical simulation. You may see this scene in the paper as well as other city scenes. Of the most complex scenes that we run wave simulation scene is this office scene, visual rendering on the left and wave simulations on the right. Signal coverage simulation as before, with a top-down view. The intensity of light that reaches the floor is visualized. We do the wave simulation in a full 3D setting, exactly the same geometry as on the left. No simplifications. 5 gigahertz Wi-Fi-like emitter on the top right, and you can see light diffracting several times, interacting with the scene, and so on. Things that are extremely hard to do with existing tools. See the paper for additional scenes and performance data. To conclude, I explained our design choices in generalizing the path integral. We have seen that bilinear frameworks, the most common way to do wave simulation today, fail to scale. We then generalize to a unique, weakly local incoherent formulation, where we go from rays to elliptical cones, and we go from interactions at local points, classically, to wave interactions at regions. Incoherence is a powerful tool. Unlike other techniques, it means that we may apply classical sampling techniques, like local path building, path guiding, path reuse, and so on, virtually in an unchanged manner and at no penalty in efficiency. And this is the point of this research. We bridge the gap between these powerful computer graphics sampling techniques to wave simulations. Some future directions, I won't go into details. We do want to take a look at acoustics and inverse simulations and some other things. That's all. You have QR codes for the release software. Thank you.